So let's pretend for a moment. We want to pretend that we have two amino acids and they're neighbors. They're next door to each other. And they come out to their yard and they begin to have a conversation. And one amino acid looks at the other amino acid, and that amino acid looks at the other one, and they find each other kind of attractive. And they're both single, so this is perfect news for both amino acids. And in the future, they see them basically having a family and little bitty amino acids running around in their yard. Okay, well, two amino acids can hook up together that way. Not a problem. And let's see why. So let's take the structure for one amino acid. So we've got this C double bond OOH, and then we have this alpha carbon, and this also has a NH3 group on it that's positive, and then we have this random alkyl group. Now at physiological pH, this hydrogen is also removed, and this has a negative charge on it. So this is one amino acid, and it comes near another amino acid. So I'm just going to draw another amino acid here at physiological pH. And then we have this NH3 plus and this R group. And I'm going to put R prime here. That dash basically means that those R groups can be different or they can be the same. So R and R prime, they can be the same if they want to, or they can be different R groups. So again, that is kind of what defines the amino acid. So it's whatever R group that goes on at that position, that is what makes all the amino acids different. The basics of the amino acid backbone is what we can call that. It's all the same. It's a C double bond O, a carbon, and an NH3 plus. Now I want you to take a look at these two structures, and I kind of want you to go back for a minute and look at the basics of organic chemistry, because the basics of organic chemistry, it's not going to change, people. We have a positive area and we have a negative area, and this positive area and this negative area will be attracted to each other. So we have a positive area that is here on the NH3 group, and we have a negative area that's here on the oxygen, and we see an attraction that can happen between these two groups if we do have multiple amino acids in solution. So they have this natural attraction to each other. A negative oxygen end, a positive nitrogen end. These two amino acids kind of come together in proximity, and a reaction basically happens between the two amino acids. And what we get are little children of H2O that get spit out of this entire thing. So if we eliminate water, and that's very important, because we've got to eliminate something in order for these two molecules to hook up. If we eliminate water, look at what happens. I'm just going to draw the two things closer together this time around. So we'll do a C double bond O and O, carbon, NH3 plus, and a R group. And then over here I'll do an NH3 plus, carbon, C double bond O, O, and an R group. So if these two areas come together and we get an elimination of water, that means that this oxygen has to disappear, and two of these hydrogens have to disappear as well. And this leaves me with an N and an H that's left over. And this is the connector point. So this amino acid is connected to the nitrogen, the amino end of this amino acid. And when this begins to happen, we get a peptide bond, and that is what we call that magical little bond that happens here between the two amino acids. So this is called the peptide bond. So this bond connects the amino acids together. Now, we've mentioned this peptide bond before, so here we're mentioning it again. So there's the two amino acids that are being hooked up by a peptide bond, and this peptide bond is formed because we have eliminated water out of the mix. Now, what I've made here is a dipeptide. And it's not surprising that this can continue on. So I'm going to put ... here because another peptide bond could form at this location and another amino acid could hook up at that spot. And then I'm going to put also a ... in front because this amino acid, maybe that's not the first amino acid of this long chain that begins to develop. Maybe this is maybe somewhere in the middle. So we can have another amino acid on this side and it can continue to grow and grow and grow and grow. But those are called peptide bonds. It's this new bond that's formed to basically take my first amino acid and another amino acid and it hooks them up together. So they go off, they get a happy little marriage and they have some children and everybody is happy, it seems like. So that is the formation of these peptide bonds. Now there's some terminology that we have to kind of go over. First, what if this is the very first amino acid in the chain? We have a proper term for that, and that's called the N-Terminus. And you can kind of see why we call it the N-Terminus, and that's because this is our nitrogen-containing species. This is our full-blown NH3 amino acid. So this is what we would call our N-terminus. This is our beginning amino acid. So this is our very first amino acid in a long, maybe chain of amino acids. The one on the end, and in this case it's just a dipeptide, so we'll only have two choices. But the one on the end will always end with the C double bond OO, and there'll be nothing else after that one if this is truly the end amino acid. And we call this the C-terminus. And this is our ending. So this is our very last amino acid. So we have this N-terminus and we have this C-terminus, and that is how we refer to those amino acids that are hooked up in the chain. Something else that we have to talk about as well is the way that they will begin to draw these dipeptides and polypeptides for you. And there's a slight difference here that you've got to pick up on because it's very important. So let's say that we get alanine and glycine and valine and histidine. Okay, so there's 4 amino acids, and if you look very carefully, I've separated them by a comma. Now that's important. I know that sounds kind of silly, but I've separated them by commas. And what that means is that here are your choices of amino acids, and they can be in any order. Okay, the commas, that's what those represent. That means here are your choices. Now you take these choices and you've got to figure out how they actually hook up in the order that they hook up in. So that's the purpose of the commas. That's completely different than if I had done ALA, GLY with a hyphen, VAL hyphen, and HIS. That, ladies and gentlemen, represents a specific order. They are basically letting you know this is the order of which they hook up, and you cannot change it. So the commas and the hyphens are very important. I know that sounds kind of silly, but that is basically meaningful when it comes to these problems, and you're going to see that in these example problems, and you're going to see that in future lecture videos. So in the comma formation, these are your choices that are laid out on the table. You have to piece them together. And in the hyphen notation, we're letting you know that this is the way that they are hooked up. This is the order of which you have to take them, and you cannot change them around. So very, very important. So take a look at that. One comma sequence is unknown, and in the hyphen version, the sequence has already been determined, and we're trying to tell you that sequence. Something else that we need to talk about as well as far as the structure of a peptide bond. Uh, Notice this is the alpha carbon, and this is also an alpha carbon, so we have two alpha carbons here. So we can call that the alpha carbon. This oxygen's got some free pairs of electrons. We see a double bond notation there. The nitrogen here also has a free pair of electrons at the same time. So this pair of electrons can move toward another bond, and that can move up toward others. And we see delocalization that can happen right in here. So delocalization, we said that anytime delocalization can happen, we bring stability to the molecule, and this makes the molecule very happy. So delocalization can go on. Not only that, but this is a very flat area of the molecule. So if you take a look at polypeptides, or you take a look at how these amino acids will begin to hook up, well, each peptide bond is basically going to be a flat area. So this flat area, that can become importance a little bit later on. The R groups that are bonded to the alpha carbons also alternate. So really, if I wanted to draw this a little bit better, what I should have done is I should have realized that molecules like transnotation, they like for these R groups to be in opposite locations. So really, if I wanted to draw a more stable structure, I should have put the R group that kind of points up here, because this one points down. And the same thing goes for the carbonyl group. You know, this double bond O, I'm pointing up. Well, in this case, I probably would want to kind of point that down to get those oxygens away from each other. So we see this trans orientation that happens as these peptide bonds begin to go and attach to themselves. The next amino acid, well, that R group would point down, just like the first one, and the C double bond O would point up, just like the first one. So you see these alternating locations as they go through. So you alternate them. You know, I'm not really particular on that. If you draw them all in the same orientation, I will be okay. However, sometimes the homework assignments, the quizzes, maybe some of the test questions, if you're doing those on Blackboard, all of those questions will probably focus on alternating these R's and the carboxylic groups and everything else that's in between. If you do that on a test, though, that I give you in class, I don't really care. As long as you've got the bonds there, the atoms that are there, as long as you've got the full-blown picture, it doesn't really matter if you remember to alternate them or not. So that's really a personal preference, but they do alternate back and forth. So pretty important. Okay, so that's kind of the inside of a dipeptide, or the formation of a dipeptide. And after the formation of a dipeptide, we can then go in and talk a little bit more about what we call primary structure of proteins. So this is just the beginning. We will keep following through. We will keep expanding on this topic in upcoming videos. So stay tuned. This is just kind of like the cream of the surface, right? We need to get really into the details, nitty and gritty of it. And that's what we're going to do in the upcoming few minutes that I have with you left in the world of amino acids.